part 3 of the development of the Class B audio amplifier. I want to keep it quite short. My camera stopped suddenly and I never do say editing afterwards. So this is the circuit that was finally working. Most important thing was this here. There are two potentiometers here, this one and that one, and they set the proper bias for the end transistors. That was very important. So in fact we have here a 1 transistor driver unit. This is the first transistor that amplifies. This is the second transistor that acts as a driver. It has 3 diodes here in its collector lead. It drives 2 Darlingtons, one say for the positive part of the sine wave and one for the negative part of the sine wave. And at the same time I realized that that is a very sloppy explanation of how such a circuit works, though it is okay. These transistors, diodes, set a certain voltage drop, and because we have here a Darlington now, each silicon transistor needs approximately 0.7 to 0.8 volts to work properly. 2 of them approximately 1.4 volts and somewhat higher, so to be driven out properly to get say a signal out here to the via the end capacitor to the loudspeaker. That means that we need here 3 diodes. You can try 4 diodes. You will surely see that immediately the quiescent current goes very high. And with one diode less here in that row, you hear distortion. The transistors are not driven out properly. I will say stand still now one moment by that schematic. There are of course say many things to further develop in this circuit. It needs much more research. I had a small problem of oscillation when the input impedance here, the input resistance, was not connected, and that's the reason why I connected here this 470 picofarad capacitor between the base and the collector. That's say a standard solution against oscillations in a transistor circuit. And now between the base and the emitter, but perhaps I had to do it between the base and the collector. Perhaps that will give better results. So there are say many things to study about this circuit. So it needs much more research, no problem with that. Output approximately 15 watts. And perhaps I can demonstrate again, say, the effect of the diodes here. But it's more important that we now have here a kind of way to set the quiescent current through the end transistor stages. And this is one Darlington and this is the other Darlington. This say for the positive part of the sine wave, this for the negative part of the sine wave. Anyway, you can set here with that 470K potentiometer the quiescent current, and here also, so there are 2 possibilities. When you drive them up too far, the current through the end transistors will get extremely high. That can damage your end transistors, but I've used by purpose very sturdy transistors to make this circuit. So anyway, you can do experiments. Let's see and listen and look. We are now on 40 volts. Circuit works between say 24 volts and 40 volts. And I had to use here a BD139 as a driver transistor. So here, because the original transistor, the BC547B, got too hot, but I left this transistor in the circuit. That is the BC557B. It's a PNP transistor. This is an NPN transistor. They both form a Darlington, and in fact we have here this Darlington driving two Darlingtons. And finally to the loudspeaker. In my earlier experiments the problem was that the driver transistors, the first transistors in the Darlington, got warm, but the end transistors did not get warm. They kept cool. That means that there is no current flowing. In such a circuit, both transistors here and transistors must get equally warm. When they are not getting equally warm, you surely know that one transistor is not in the conducting stage, so it doesn't amplify when we are talking about audio. And now it's okay, everything works. So let's say when you do experiments and also want to develop a Class B audio amplifier, that is the best idea. And again, I've used very sturdy transistors, the BD744C and the BD743C. They can handle approximately 7 ampere, and that's of course the maximum current that they can handle anyway. And here I've used them again as kind of drivers in these two Darlingtons. This is one Darlington here and this is the other Darlington, etc. Let's listen to the music. That was too fierce. You hear the audio distortion. Anyway, it works good. I think the music is in Albany, New York. This is the music, by the way. I always use it. I did not use this, but I used here in Albany, New York. So, well, let's see what this circuit can bring, and especially when we change here the bias of the end transistors, the two end transistors. And I will now turn this potentiometer. Let's see what happens in a current. So you can surely hear the hum, maximum current. That's very bad, of course. So you can set here with that potentiometer the quiescent current, and also here do the same thing. Exactly the same problem. That means that the whole stage, the transistor end stage, works properly, is properly driven, because the two stages here act symmetrical when I change here the bias to the end transistors. I cannot play another music. Perhaps this is not copyrighted, the music signal that follows. When it is When it is not that, I will stop the music. Again, the music is playing again the same tune. That's good. So it works, and there are of course many things to do. I'm going to do an endurance test. Say connecting here a car lamp, maximum voltage, maximum current, overdrive the transistors, let the heatsinks get extremely hot to see if the circuit is stable enough on the longer term. That's also very important with an audio amplifier. Say it must endure all kinds of critical situations. Too hot cooling plates, overdrive at the input, etc., etc. It must not start to oscillate. That's also still a problem that I have to encounter somewhat better. But perhaps this is interesting. Now you hear the hum from the loudspeaker, and when you make an audio amplifier, this is always a good sign. Say a faint hum on the background, and when you touch the input here, this is always a good sign. And why is this a good sign? Because you don't hear distortion, you don't hear kind of screaming sound, you hear a quite stable hum on the background, etc. That's very important. So let's look at the scope, also important. As a first test, touch the input of the amplifier with your finger, look on the scope. And here you can already see the properties of your amplifier when you simply touch it with your finger. So here you see, for instance, that even with my finger that has on my body, I have an extremely low, say, input voltage to that amplifier. You can see that this amplifier amplifies very much, and even tends to oscillate. You can see it here. So there's a tendency to oscillate, and that is perhaps one thing that I have to cure. Of course, when you make such an amplifier in a stable way, and then I'm talking about the wiring, everything very stable, the tendency to oscillate will be much lower. But like I told, I make circuits that everyone can make, and even on such a simple way on a wooden breadboard with brass nails. Let's look again to the scope. Where are the oscillations visible? Now I touch with the other part of my hand another part of the circuit. So I bring down the amplification somewhat and lift up the, say, the time base to see where these oscillations are, approximately on which frequency. Now I bring back the time base. So anyway, I don't will dig too deep in this matter. The whole circuit is healthy and real. It works properly, and even with, say, properly working chips, other audio and amplifiers, you will see the same issues when you do the same test with the scope and your finger at the output. Thanks for watching. In part 4 I will publish the definite schematic with all problems cured.